For those of you who don't know, well, while my background is in electronics, I've been programming since late middle school. While I say I've been programming, I wouldn't say I was a programmer, and that's mainly because, for the most part, I was self-taught. That's not to say that self-taught programmers aren't real programmers, but it's more like I never really felt like my skills as a programmer were adequate enough to be called one. And the reason why I felt this way is because, while I was very good at making small projects, if the project grew too big, it quickly got out of hand. Now, in my earlier days, this was mainly because I would write code procedurally and imperatively. Procedurally meaning the program reads off like a laundry list of instructions. Do this, then do this, then do this. And imperatively meaning state is declared, modified, and used wherever. And if you know anything about programming, you'll know that this is probably the worst way you could organize your code. However, as I studied further, I did eventually learn other methods of managing larger code bases. Things like structured programming, functional programming, and even object-oriented programming. While these did help quite a bit, it still felt like there was a ceiling I was hitting, where no matter how many functions and objects I made, I still couldn't quite manage my code. Case in point, one of my larger projects I took on around this time was a recreation of Pac-Man. I made this around the time I was learning about objects, and the use of classes and objects did help keep things organized. But I only just barely made this program work. The code under the hood is very poorly written. It was extremely rigid and didn't have much room for improvements. And what's more is, despite my best efforts, it was still pretty buggy. Now this was a problem, and I had recognized it as a problem, and my assumption at the time was that I just wasn't keeping my code organized. So I continued my self-study. I found other techniques, practices, and paradigms. Things from the solid model to test-driven development to design patterns. If you were to ask me to recite design patterns or the solid principles from memory, though, I wouldn't be able to tell you. And that's mainly because there's a lot there to understand, and for me it just wasn't clicking. Well, that's not entirely true. There was one thing that clicked. Test-driven development. The idea on paper was sound. You have more freedom to change your code if you can verify that everything still works after everything has been changed. And the best way to create that verification system is as you build your project. However, being new to the idea of TDD, there was an issue with the tutorials I found. Take a look at these.
Suppose you ask an engineer to write a function that computes the area of a circle, and with a single line they compute and return the area. Let's test the values. 2, 0, -3, 2 plus 5j, true, and the string radius. The area is correct for a circle of radius 2. But wait, what's this? The function computes the area of a circle with a negative radius. The first will be test_area. Here we will check that the function correctly computes the areas of several circles. Let us also check the function works for a circle of radius 0 and a circle of radius 2.1. Run. We see the test ran and everything is okay.
So if you're not currently testing your code, then it's definitely something that you're going to want to learn and start adding to your projects. And I want to start off using these really simple functions so that we can just focus on what the tests look like. So let's write our first test. So I can run our add function from here by saying something like result is equal to calc.add. And now we want to assert that that result is equal to 15.
Let's actually run to what a test may look like for this. So I'm going to drop down the creation service. We kind of have a good sense of what that is. But let's go ahead and test that. Let's go ahead and test the Tesla method. So first, let's go ahead and write a test for ensuring that the make is correct. And then what we're doing inside of here is we're calling that creation service. We're storing that in a result variable. And then we're saying that result should equal Tesla, should equal the string Tesla.
What should it do if we pop an empty stack? It should throw an exception. Will throw underflow when empty stack is popped. Here we want to say stack.pop. Oh heavens, I don't have a stack.pop. All right, so I should create the pop function. Void? No, it should return an int. Okay, 0. I don't like 0. Let's return -1. Okay. Run the test. Oh, test fails. Why? Because it expected the exception. All right, I need to throw the exception. Well, okay, I can do that. Throw new underflow. Yeah, okay. Oh, heavens. Okay, now I don't need the return. This should pass. Pass. Okay, good.
In all of these examples, they made it seem like the tests were supposed to be applied to each and every function or method in your codebase. If you write a method for a class that produces a string, you'd better have a suite of tests that verifies that behavior. It didn't help that I was using Mojang's Brigadier library as a reference at the time. And from what it looked like to my newbie eyes, they had their tests organized similar to their production code structure. After seeing this, I figured that this was how the big boys write their tests, and that's the way it's done. I tried implementing this style of testing for a bit. I even tried it on my own redstone development kit, though decided against it because I thought that it was too much work. If you look at the code now, you may notice quite a few gaps in the test suite. That's because I quickly realized a flaw in this system. If you change anything, absolutely anything in the structure of your code, then you must update your test suites, and more often than not, those updates to the test suites are quite extensive. I quickly abandoned the idea of using tests and just stuck with writing code as usual. I still wasn't very good, but I could usually cobble something functional together, and as previously stated, the use of classes and functions at least helped quite a bit in allowing me to make more complex programs. And that was the level of programming that I operated at ever since. That is, until I found this video. For those of you who haven't seen this is the RPC3 project. It's a hex-based computer built by CT5K, and it's gotta be one of the smallest execution units I have ever seen. Now, notice I say execution unit and not computer. And that's because this computer is missing any form of control logic. Regardless of the shortcoming, though, it's still a really cool project. This sort of issue isn't exactly a difficult thing to overcome, so I decided it would be a fun project to design a computer around this execution unit, just to see if I could. So I took a bit of time to research this execution unit and learn how this device worked, and I immediately ran into the project's first hurdle. See, the execution unit has 6 instructions it can execute, that being load register A, load register B, clear register A and B, add A and B, negate A, and clear the output register. It sounds simple enough, but if you look at the adder circuit for this device, yeah. Addition was limited to a range of 0 to 15. Now this makes sense for hex, but if you add something like 8 and 9 together, you should get a result of 17. Capping the answer at 15 doesn't help here. The problem is especially apparent when you're subtracting numbers, as subtraction in a logic system tends to take advantage of integer overflow. For example, if I were to remove 1 from 8, well, that's the same as adding -1 to 8, which is the same as adding 15 to 8. This equation results in 7, but only if you have an overflow. Now this was something that CT5K said wasn't an issue. He had mentioned that you could perform subtraction with this device.
If we add some wiring for the variables, we can do not A plus B, not A plus B, not B plus B, A plus B, and A minus B, just to list some examples.
But I wasn't seeing a way that it could be done. So I brought this to his attention, and after some back and forth, he taught me an algorithm that could handle overflow and underflow conditions. I tested this algorithm in a spreadsheet, and sure enough, it produced the correct answer. But there was a problem. It used subtraction. So I needed to subtract in order to subtract. Fortunately, CT had a solution for this as well. Apparently, inverting the minuend, adding, and inverting the result is the same as subtracting. I again plugged this into my spreadsheet, and it did work, but at this point one should wonder why there wasn't hardware to handle this already. Regardless, it was around this time that I got the idea. In order to know with 100% certainty that this algorithm worked, I would need to test every combination of hexadecimal inputs and verify their results. With 2 inputs and 16 possible states for each input, that's 256 possible combinations, and I wasn't planning on doing that manually. So I wrote a quick Python script to test this for me. I first had it cycle through all combinations of inputs A and B, then I had it sum the 2 numbers with my special algorithm, and then again normally, then compare the 2 answers. The result would either be correct with an overflow or underflow, or completely wrong. I ran the program, and sure enough, the algorithm worked. With a greater sense of confidence in this new adding algorithm, I then converted this algorithm into a sequence of instructions that the RPC3 unit could run. Doing this was painfully tedious to say the least. Every time I needed to invert a number, it involved shuffling around all 3 registers, and there was a lot of inversions that needed to be done. But I did eventually get my sequence written. Now all I needed to do was see if it worked. Now, normally around this time, I would build a prototype computer, test it, and then make a note of any changes that needed to be made. But this time I figured, hey, why not write another script? After all, RPC3 was simple enough. I could emulate it in code pretty easily. So that's what I did. I wrote a basic class that would emulate the RPC3 execution unit, converted my sequence of instructions into a sequence of method calls, and then ran the exact same test as before on my new algorithm, and sure enough, it failed spectacularly. I'm rather glad I got this feedback so quickly and with such little effort invested into verifying this algorithm works, because if I had gone my traditional route of testing by prototyping, it would have taken me weeks to get this algorithm sorted out. Anyway, I debugged the sequence. Turns out there were numerous occasions where I had forgotten to clear a register. This whole clearing before writing thing was not something I was used to. But once those fixes were in, I tested it again and everything worked out flawlessly. So this is great. I have an algorithm that can perform proper addition, and I have a sequence of microcodes that will execute this algorithm, both of which I know to be 100% functional. For those of you curious though, yes, executing addition on this computer takes quite a number of steps. 26 to be exact, and that's if there's no carry. If there is a carry, it takes 32 steps, 32 microcodes to execute an add instruction. This does seem a bit excessive, but again, I was just doing this to see if I could. At this point, I had started adding more instructions to my instruction set and using my test environment to verify that they were working until I had a complete instruction set and a complete set of microcode sequences that would execute these instructions. I had also finalized the system architecture by this point, so not only did I know what microcodes needed to be produced, but also what control signals needed to go with each microcode. Now all that was needed to be done was to create the state machine that could produce these microcodes and control signals. Now I've had some experience designing state machines, so writing that up wasn't too difficult. But of course I needed to test this design before officially incorporating it. Again, the thought had crossed my mind to build a prototype for testing, but then I figured, hey, we've already got most of the computer emulated in Python, why not write up the state machine too? So that's what I ended up doing. I wrote a new test suite that, this time, verified the functionality of the computer system as a whole, rather than just testing its parts. I then plugged the state machine in and tested it, and after some debugging, it ended up working perfectly. Now by this point, I had a fully designed computer, and its architecture was fully tested. I could start building at this point, but I wanted to simplify some of the control circuits I had made. I had a few ideas to simplify them, but again, I needed to test them first before I could say they were good to go. Fortunately, I didn't need to rewrite my state machine. I just needed to change some Boolean expressions representing my logic circuit to implement these changes. I ran the tests again, and just as I expected, everything still worked. That was when something clicked. If I had written a test that verified the sequence of the control signals coming from the state machine, I could make the changes I had just made and the test would still be able to verify the state machine's behavior. But what if the state machine's behavior were to have changed? Or what if I ended up not needing a state machine at all? Well, then I would have to rewrite my entire test suite for the state machine in order to verify that everything still worked. Fortunately, though, I wasn't testing the state machine's behavior. I was testing the computer's behavior as a whole. While you would think that testing the system this way meant that I didn't have good test coverage, I didn't think this myself. Granted, I'm not directly verifying the behavior of the state machine, but if the state machine was misbehaving in any way, it would result in the computer system as a whole not behaving as expected, and my behavior tests at the top would detect that and indicate that something was wrong. One of the more personal projects I've had on my docket for a while now was a small tool that can pull transaction information from receipts that get emailed to me. And this would obviously help with my weekly accounting process that I do. And so this tool, if I wanted it to perform this task, would likely need to have four key features. The first being the ability to read emails from my email account. The next is to be able to parse those emails, which means I'll need to be able to list and modify those parse rules. I'll also need to be able to use those parse rules to generate transaction reports from those receipts. And obviously, I don't want to be rewriting my parse rules all the time, so the ability to save and load profiles would also be helpful. So with those four key features in mind, I was able to identify some user stories, which are non-technical descriptions of what the program should do in certain scenarios. And then using those user stories, I basically created my test suite here. And as you can see in my tests, I have folders that represent the different features that I wanted. Inside those folders are the different test files that represent the different user stories. And each user story has its set of acceptance tests. Sometimes it's just one. In this case, we have a number. But these acceptance tests are written in a way that it's very easy to understand what it is we're testing here. So for example, test bypass unsaved changes warning when creating new profile. As the user story would suggest, this whole test suite here is to verify that after the user's been warned that they might lose data, the user can proceed past that warning and perform some kind of a command, either create a new profile X or load a new profile, regardless. And so as you can see, when we create our accountant instance, we tell it to create a new profile, modify it, then we tell it to try and create another new profile, bypassing the warning, and then verify that that's been created. And the reason why my tests are so clean versus the code under test is so dirty is because I have this this sort of 3-layer system. It's not quite the 4-layer system that's recommended, but I have this test environment class that sits between the code under test and my test suite. And this basically just acts as a translator for all the intended actions. For example, if I want to create a new profile, I can call this in any sort of test, and this test environment will then translate it into the appropriate method calls for the code under test to actually perform that action. And with all those tests written and with all those tests passing, I know for a fact that this program is working 100% as intended. And if you're concerned about test coverage, again, obviously we're not really directly testing the code here. We're testing sort of a test environment. You would think that test coverage would be an issue, but that's not true. I have a coverage report here, and you can see we have a 98% coverage report here, which 98% coverage just by testing the behaviors at the highest level is actually pretty impressive. In other words, I didn't have to write a test verifying every single function and class method to know my system was working. All I needed to do was write just enough tests to verify the behavior as seen by the user. Because to the user, the behavior is all that matters. And for a computer system, its behavior is this. The user gives it a program, it runs until it halts, and the computer is expected to use that program to manipulate memory in a predictable way. The user doesn't care if the computer is a pipeline system or an out-of-order execution architecture. They don't care if it's a von Neumann or a Harvard model. They don't even care if the state machine has one set of control expressions or another, or even if it has a state machine at all. The only thing they care about is the program goes in and data comes out. And so that's what I should be testing. And that's what I had been testing. I wrote tests that verified only things that mattered at the end of the day, the machine's behavior. This has other implications too. Because the tests simply verify that the behavior works as intended, I could draw up a whole new computer architecture, plug it into my tests, and the exact same tests would be able to tell me if this architecture worked or not. This idea of testing behavior, not implementation, and the ability to change implementation without needing to change the tests doesn't sound like much. But this was huge. In fact, this is exactly what I was looking for. I began using tests like these to guide my software design, and what I found was suddenly, for some odd reason, all of the programs that I had been struggling to build for the longest time were suddenly being built within a few days. What's funnier too is during this period of exploration, I found myself writing worse code, almost reverting back to the sequential imperative code. But it didn't matter to me, because the tests were passing. And so long as those tests were there, I could clean up the code, refactor it, and the tests would tell me if everything still worked. It was because of this, by the way, that I was tempted to title this video, "I'm much better at programming now, and my code is worse than ever." Looking back at this, though, from this newfound perspective, I think the reason why I struggled to organize my code effectively, and why things like the solid principles and design patterns didn't stick, is because I was trying to organize code that wasn't fully developed. I was trying to give shape to something that did not yet have a shape. This may sound counterintuitive, but more often than not, what I found myself doing in those situations was taking an underdeveloped idea and trying to find, quote, the perfect structure to hang it on. And what would inevitably happen is I would find that the structure I had envisioned didn't account for some edge cases. This would lead to patchwork, which would increase the complexity of the code, making it harder to work on, and eventually the code would just fall into disrepair. As previously stated though, if I had tests that could verify that no matter what implementation I used, the code did indeed work, well then if my code ever became too unruly, I could clean it up and quickly verify that everything still worked. In the design process, though, this gives me tremendous amounts of freedom to just build what works, and not worry too much about organizing my code. The end result is, by the time I get to the point where most of the tests have been written and are passing, the only thing that exists in the implementation is exactly what I need. No more, no less. Getting this bird's eye view of the system in its most raw form can then allow me to see exactly where points of articulation need to be located. In other words, it's easier to see what structure would support this idea once the idea has been fully formed. The tests, then, are not methods of organizing code, but organizing behavior. If the tests were written well, I could get a bird's eye view of what the system needs to do, and then start working on the system that met those behavioral requirements. Now, I'll admit, this is still one of those only on paper type ideas. I have been using the system in my own projects as of late, and I can say that once you have a good set of acceptance tests defined, building your code becomes a whole lot easier. But defining those acceptance tests is a challenge in and of itself. One issue you may run into if you decide to try this is even though testing the behavior decouples your tests from your code, it's still coupled to the interface details of your code. Meaning if your interface changes, the tests have to change. And depending on how many tests you have, that can be a nightmare. Another issue with this is more of a philosophical one, but it's more what counts as behavior. For example, say I wanted my program to take commands from a user and modify the value in a database. That's behavior, right? You could write tests to verify this behavior, but what if your command structure changes? Well, then your tests will no longer pass. Even worse, if you decide to ditch command inputs and go for a graphical input instead, or you change the database into a cloud system, well, then the tests have to be rewritten. This is one of those cases where it seems like you're testing behavior, but in actuality, you're testing implementation details without realizing it. There's a channel that I follow that offers a lot of solutions for these kinds of problems, and if you're interested, I would highly recommend checking out the channel Continuous Delivery. He has a lot of great videos explaining these sorts of pitfalls when testing, and what to do to avoid them or remedy them. In particular, something of his that addresses these two issues specifically is his talk on a testing framework.
So here's our system under test, and here's our test infrastructure surrounding it. And typically, in this kind of scenario, if we've got some notion of time in our system, somewhere there's going to be something that looks vaguely like this in the code of the system. We're going to have a call to system get time or its equivalent in whatever language or infrastructure you're using. Again, we solve this kind of problem by introducing a level of indirection. So instead of you calling directly into the system, we put our own clock in the way. So instead of asking the system for the time, we're going to ask our clock for the time.
Now granted, I didn't implement his solution quite to the degree of detail that he describes. But even with my simpler 3-level system, it's still a huge help and has improved my ability to identify behaviors I would like in my systems, as well as testing them to ensure they work. So yeah, that's my journey as a programmer. It's been a long one, but now I have a tool for articulating the desired behavior of a program, and it seems that in the grand scheme of things, that's the most effective tool to have in your programming arsenal. Even though I don't really have any algorithms memorized, or have an understanding of design patterns or other programming principles, or really any understanding of any programming environment apart from a local executable, and probably couldn't answer a single question in a technical interview, despite all of that, I think I can now say with a fair bit of confidence that I am indeed a programmer. So what do you think? If you're in a similar situation to what I was in, do you think this might help? If you're a professional, do you think I'm missing anything? Feel free to stop by my Discord if you want to have a discussion about this. I'd love to hear your thoughts. Or just leave a comment, that's fine too.